I want to give you a simple intuition for the Green's function. Let's say you know how to solve a simple differential equation, like Laplace equation. Now let's say you have a more complicated equation, like this one, with the inhomogeneity f of x and the weird differential operator. What to do? First, let's reboot our brain. Why is a differential operator anything special? If it's not special, we can just divide by it. Then we get our solution very easily. The derivatives cancel out on the left side, and on the right side we get 1 over derivative operator times f of x, or the inverse. But what is this object? What does it mean? We can say that in some way the integral is the opposite of a differentiation. So we will do exactly that. We take the integral over the whole domain and then integrate. But over what? We need to integrate over dx prime, not over dx. Then of course we need to have our function f of x prime, and we need to add some other function that somehow takes f, processes it, and gives us our solution. That function is g and needs to depend on x prime, because we integrate over x prime, and also needs to depend on x, because we have no x dependence yet. But what is g? We exchanged our old with a new problem, how to determine this function. Now we can, because we have the solution written down, insert it into our differential equation. So we do exactly that, and we have the differential operator times the integral, which contains the Green's function and also the inhomogeneity f of x. We can now exchange the differential operator with the integral. And if we do that, we write down the integral of the differential operator times the Green's function times the inhomogeneity. And from the differential equation, we know that this has to be f of x. This equation is satisfied if the curly brace equals the Dirac delta distribution. If we integrate the Dirac delta over a function, we get exactly the function back. That means that now we have a differential equation for the Green's function. We have the differential operator times the Green function equals the Dirac delta distribution. Remember that we did not use any specific property of the differential operator except that the inverse exists and that it exchanges with the integral. That means that for any differential operator L, we can find the Green's function that satisfies this differential equation. And this means that we can also calculate the solution with the Green's function and the integral. Congratulations, now you know where the Green's function comes from and what it is, why it makes sense. Now you still don't know how to calculate it, so we still don't know how to actually solve the differential equation, but I will show you an example in a future video. Thank you for listening, and I hope this will be helpful to you.